All right, hello everyone. My name is Jesse. I work on the PyTorch core performance team at Meta, where we work on making your models run as fast as possible. And I'm here today to give a lightning talk on fast sparse vision transformers with minimal accuracy loss. All right, perfect. All right, so what are we gonna talk about today? First off, I'm gonna talk a little bit about sparsity, what it is and why I think it's interesting and why you should care. And then we'll talk a little bit about the two subproblems within sparsity. The first one being acceleration. So basically, if you have a sparse model that has a lot of zeros, how can we skip computation and make that model run faster? And then there's a corresponding second problem, which is accuracy. If you have an existing model and you want to make that model sparse and put a lot of zeros into that model to speed it up, how can you do so in a manner that maintains your downstream performance? And finally, we'll talk a little bit about how you can take advantage of the work that we've done and speed up your own models with sparsity with just a couple lines of code. Okay, so what is sparsity? As eloquently put, right, why waste compute, use many parameter when few parameter do trick? The idea here is basically, if you have zeros in your model, you can skip that computation, and that should speed up your model. And the way I like to think about this is it's very similar to quantization, which is another model optimization technique. But in quantization, right, you keep all of your parameters, but you shrink the precision of each parameter. So you go from float 16 to int 8, right, and you speed up your calculation that way. In the case of sparsity, you keep the precision of the parameters the same, but you're removing chunks of parameters from your model in a structured manner. And this is a really old idea. It dates all the way back to 1989 with this Yan LeCun paper. But I think it's particularly interesting now because of the rise of these large Gen AI models that have billions of parameters. So we have a lot of options to pick from for things to remove. And also reducing these compute and these models that require a large amount of compute and memory, we can reduce that overhead with sparsity, which makes it attractive. Okay, so how does accelerating a model with sparsity work? So the key idea, right, multiplying by 0 is really fast. 0 times 123,000, right? You can figure out the answer to that in a second versus the operation on the right. But the thing is that depending on how you do this calculation, you might not actually be faster. And what I mean by that is if you multiply 0 times 3, right, and then go 0, and then you carry the 0, and then you do 0 times 2, right? If you do your multiplication that way, then it's not actually any faster than the calculation on the right. And so what you have to do, right, is you have to skip calculations with the 0 parameters. And the way that you do that is, you can see on the diagram on the right, like, assume we have some way to put the zeros in the matrix. What we can do is we can store this matrix in a way such that the non-zero datas are stored separately from the metadata. And the metadata gives you essentially the structure of the matrix. And then once you store the matrix in this way, what you can do is call into a really fast sparse kernel that takes in the matrix in this kind of split format. And this sparse kernel will avoid doing computation with the non-zero elements, or with the 0 elements, and just work on the non-zero elements. And then it will use that metadata to restore the structure so that the results are numerically accurate. So this is like a matmul optimization. We targeted the NN linear layers of VIT, but you can really apply this to any kind of model that you have. All right, so for sparsity, as I mentioned, there's kind of two components, accuracy and acceleration. And these are kind of competing factors, right? So if you replace your entire model with a 0, right, it's very fast, right? But the accuracy component is quite large. So there are specific GPU sparsity patterns that basically exist in like a Goldilocks zone where they offer a good amount of performance, right? But they're also relatively easy to find accurate subnetworks for. And the two sparsity patterns that we really care about are semi-structured sparsity, also called 2-4 sparsity, and block sparsity. So in semi-structured sparsity, 2 out of every 4 elements will be 0 in this 1x4 tiled strip. And basically, NVIDIA added hardware support for this in their Ampere architecture. So they've also published libraries and fast kernels in order to accelerate 2-4 sparse matmul. And then for block sparsity, it's a little bit larger. or the block size is a little bit larger, and then you're zeroing out blocks at a time instead of within a single block, as you can see here. And another thing I'd like to mention is that for 2-4 sparsity, we're at a fixed sparsity level of 50%. But for block sparsity, right, your sparsity level can be variable. It can be anywhere from 0.1 to 0.9%. Cool. So what kind of speedups can we expect to see, right? I have this little chart here that shows the kernel benchmarks across a single linear layer for VITs. And I think the key takeaway here is basically we have this dashed line at 1, right? And everything is, in general, on top of that line. So we're seeing speedups. The sparse kernel is faster than the dense kernel. And what these speedups ultimately depend on, right, is a couple of things. The first thing being the matmul shape. So like in order to set up your sparse matmul, there's a little bit of overhead. So in general, right, if you have a larger matmul, you get closer to the theoretical max speedup. And then the other thing that matters is the sparsity pattern, which I mentioned before, and that comes down to just like hardware support and also the sparsity level. So for semi-structured, the sparsity level is going to be fixed at 50%, but for block sparsity, you can have a variable sparsity level, and as you go more sparse, right, you go faster, but then the accuracy component becomes harder. Cool. So now we figured out acceleration, let's talk a little bit about accuracy. So I would say like accuracy is definitely an open area of research. There's not really one way to do this. I think it's a lot of people trying a lot of different things based off of the resources that they have at hand. And what I mean by that is kind of like going from the easiest way to do this to the hardest, right? The easiest way is you just kind of prune using like weight magnitude, and then you just say, okay, like I'm just gonna hope that this model is good enough, even though I've removed a lot of parameters that are non-zero. And then there's sort of like an addendum to this, right? You can prune and then do like a little bit of calibration, almost like quantization, or a little bit of fine tuning, and try to recover accuracy in that way. Basically, just fine tune your non-zero parameters that you preserve. In our case, we found that this worked really well with semi-structured sparsity. So NVIDIA has published a paper like in 2020 about this, where they showed that if you prune once and then you redo your training loop, then you can basically get the same kind of performance as your original dense model. For block sparsity, it's a little bit more complicated. So I think the zero shot and the one shot stuff, we don't have a good way to do that. So instead, we worked with a couple of researchers at FAIR to develop a sparse training algorithm. And the idea of sparse training is that you don't start with a pre-trained model. Instead, you start from scratch. And as your process, as you go through training the model, you make it sparse, and you get a sparse model out. And I think another thing here is that there's a lot of different ways to do the accuracy component, but really, once you get your zeros into the right place, acceleration is like the same kind of problem. And that's what we've tried to solve with torchao, which I'll talk about a little bit later. Yeah, this is just like a diagram of sort of our approach with superblock, which is what we use with block sparsity. But generally, the idea is that you have trainable weights and a trainable mask, and you learn the mask as part of your training process, and as a result, you get a block sparse weight out. Yeah, as I mentioned, this is all available in torchao now for you to use. It's really easy, just a couple lines of code, right? There's a quantize API, and this is the corresponding Sparsify API. And then you can pass in the different options for semi-structured sparsity or block sparsity. You can pass in the tile size for block sparsity. And then I'll talk about a little bit about this in the next couple of slides, but we also compose with quantization for max speedups. And we do this through the quantize API that's available in torchao. It's just a couple lines of code. You can check it out at this link here. But we're also in CUDA mode, which is a Discord. There's a sparsity pruning channel. And we're pretty active in there, so if you're interested in kind of trying this out or you need support, definitely check that channel out. Okay, so what kind of speedups do we see? We did all of our trial end-to-end tests with vision transformers on ImageNet 2012. And as you can see, right, we get about a 13% speedup with semi-structured sparsity. And then with zero-shot pruning, we get pretty good results, like 91% of the original accuracy. And then for superblock, right, we get a little bit worse performance, like 78%. I think this is because our ImageNet training script is not very good. But we get much faster speedups, up to 1.36x at a 90% sparsity. Okay, so I talked a little bit about quantization and how sparsity can compose with that. The idea of quantization, right, is that you have an FP16 matmul, right, and you want to instead express that as an int-A matmul. And I think a key insight here is if your quantization is symmetric, basically just WX, just scales, no bias factor, then your quantization is zero preserving. And what I mean by that is if you have a 0 in your weight, your FP16 weight, after you quantize it, you will also have a 0 in your int8 weight. And what that means is that instead of doing this int mm with a normal dense kernel, you can do it with a sparse kernel instead. So in torchao, we use torch.compile to generate the fused kernel. And when we compose with sparsity, right, we essentially replace the dense int mm with a sparse int mm. And that way we can compose both quantization and sparsity in order to get maximum speedups. There's another bit to this here, which is that because of limited support, we can't quite fuse and create a giant fused kernel like we do for quantization. So instead, there's been a lot of work and research done into basically fast sparse quantized kernel that are basically just a generic CUDA kernel that do quantization and sparsity all at once. And we've integrated this kernel into torchao for you guys to try. It's an int4 weight only kernel, mostly for LLMs, but this is like really interesting, and I think this is kind of where the future of this kind of work is going. Yeah, gotcha. Cool. So for results, we can see that when you compose quantization and sparsity, you get an extra 5% speed up for semi-structured and a 10% speed up for int8 with basically no extra accuracy degradation. And we also tried this on Coco, so not just ImageNet. Yeah, we get 97% of the original accuracy with the 16% speed up when using int8 dynamic quantization and semi-structured. Cool. This is just a little support matrix showing you the different options and the different supported stuff. So just feel free to check this out. And finally, I just want to say this was a lot of work by a lot of people, so I just want to give them a shout out. And I think there are really two groups of people that I'd like to reach with this talk. The first are if you are writing fast sparse kernels, definitely reach out. We're really interested in having those in torchao. And then secondly, if you're someone who's doing sparsity research and you're looking to pruning models, prune to those target sparsity patterns that we showed earlier, because you can accelerate them very easily with sort of our code. Thanks.